Hello everyone, in this video I'm going to talk about motion in polar coordinate. In polar coordinate, the position of a point can be represented by its distance to origin and its polar angle. For example, the point P can be represented as r0 and angle theta. So at here, r0 is its distance to origin and theta is its polar angle. But what about describing the motion in polar coordinate? Well, we are going to use two unit vectors. They are theta hat and r hat. And here, r hat points to the direction of this radius, and theta hat represents the angular direction, that is, which direction is going to turn. We can write r hat and theta hat into their Cartesian forms. So r hat becomes I cosine theta plus j sine theta, and theta hat becomes minus I sine theta plus j cosine theta. Now we are going to take the derivative of r hat and theta hat with respect to time. So dr hat dt is equals to I sine theta d theta dt plus, there's a minus, and j cosine theta d theta dt. And here we can rewrite this formula into this one. So this part is just becomes theta hat. So the derivative of r hat can be written as theta hat times theta dot. Similarly, the derivative of theta hat with respect to time is minus I cosine theta d theta dt minus j sine theta d theta dt. And we can rewrite it into this form. So this part becomes r hat. The derivative of theta hat can be written as r hat times theta hat, theta dot. Now, after deducing the derivative of r hat and theta hat, we can start to deduce the velocity v. So velocity v can be written as the derivative of vector r with respect to time. So vector r is just the position vector of point P. And the vector r can be written as r times the unit vector r over dt. And this r right here is the magnitude, that is the distance from point P to its origin. So it becomes r times dr hat dt plus r hat times dr dt. So this is r times r hat dot plus r hat times r dot. According to the calculation before, we know that the derivative of r hat is theta hat times theta dot. So it can be rewrite as r times theta hat theta dot plus r hat r dot. as we can see that velocity can be represented by these two terms. The first term represents the angular velocity. And this term is going to represent the radial velocity. In other words, the angular velocity means that it's going to describe the velocity of when the point starts to rotate with respect to its origin. And it doesn't influence the change in the radius. Oppositely, the radial velocity only represents the rate of change of the radius instead of the angular velocity. Well, after deriving the velocity, of course, we're going to deduce the acceleration. Basically, acceleration can be written as the derivative of velocity with respect to time. And here, velocity is just this part. So dv dt becomes r dot theta hat dot theta dot plus r times, sorry, and I think I made a mistake here. So, and here dv dt is r dot theta hat theta dot plus r times theta hat dot theta dot plus r theta hat theta double dot plus r hat dot r dot plus r hat r double dot. So we can see that the acceleration is very complicated. However, we can write it in a clearer form. So here we're going to rewrite it in this way. So we need to use the derivative of theta hat and r hat again. Sorry, I left a minus here. So the derivative of theta hat is minus r hat theta dot. So minus r hat theta dot times theta dot plus r theta hat theta double dot and plus theta dot theta hat times r dot plus r hat r double dot. Now we can write it into two parts. One part is represented by theta hat, and another part is going to be represented by r hat. So this becomes r dot theta dot plus r theta double dot plus r dot theta dot times theta hat plus r theta dot square plus minus r times theta dot square plus r double dot times r hat. So it becomes 2 r dot theta dot plus r theta double dot times theta hat plus minus r theta dot square plus r double dot r hat. Now, this formula is very important. This is the general form of acceleration. However, it doesn't mean that we need to involve all these terms when we calculate the acceleration in reality. For example, if we're going to calculate the acceleration of an object that is doing uniform circular motion, we don't need to involve all these terms. In a uniform circular motion, the path traced by this point is a perfect circle, so its radius is always constant. This means that r dot is 0, and r double dot is also 0. Also, its speed is uniform, so its angular acceleration equals to 0. So now, we can see that 2 r dot theta dot becomes 0, and r theta double dot becomes 0, and r double dot becomes 0. So we only left minus r theta dot squared times r hat. And theta dot is just omega, the angular velocity. And this is the acceleration of uniform circular motion. That's all. Thank you.